switch back to the screen once this comes back. And if you can mute yourself, especially people in the classroom. Okay, all right, okay, this should work. And if this comes back, we will switch back to the computer so everybody in Ambassador can see the screen, and then so we don't need to, yeah. So we are on slide 40 for this petitions and probability. This is where we were last time, and we will now continue to finish the probability review. Some of this will be exercises, so you will get the chance, especially some of you I know started doing homework 1 and has some questions about, especially I know the transformation of variable and how to find the distribution. So we're gonna have exercise today in here, so we're able to get some exercise, and then that can help, I hope, with the homework exercise. So in Bayesian inference, I wanted to continue here talking about the partition that we talked about last time. So this is slide 41. The disjoint hypothesis or status of nature, we have this partition of H1 through HK. And we also define this capital E as the outcome of a survey, study, or experiment. So you can think about H as those hypotheses that you might have, okay? And then E itself will be the data that you're gonna collect, and it could come from a survey, study, or experiment. One thing I would like to raise early on is sometimes, and we talked about Bayesian inference can go beyond just doing that. For example, cancer screening, we can also understand hypothesis, especially compare different hypotheses before and after you conduct experiment. So as we know, for Bayesian inference, before collecting the data, you can have what we call prior understanding or prior probability of different hypotheses. And then we collect data, and then we can have what we call posterior probability or distribution of those hypotheses. And so for us, mathematically, I want to show you, since we did that review about partitions and all that, we can actually think about H1 through HK as they are a partition, so they are disjoint hypothesis, and the union of them is the entire space. And let's see how we can actually compare different hypotheses, HI and HJ, among the capital K different ones, after we see some study outcome. Okay, so you can see that mathematically, we have this posterior probability, right, of HI given E. So E is the data part, so that's why it's posterior. Okay, and we're looking at the probability of HI given E versus probability of HJ given E. So both of them, HI and HJ, they're different hypotheses, and we have prior for them to start with, and then we arrive at posterior given the same event E. Okay. So on the left-hand side, you can see here, this is the posterior ratio of HI given E over that of HJ given E. So we have two hypotheses, okay? And then both are posterior probability. So we are looking at the ratio, and we are using this ratio to compare the two hypotheses after we see the data. So mathematically, as we know, given what we know from Bayes' rule, so you can see that on the top, on the right-hand side, we have this using Bayes' rule to actually express the posterior probability of HI given E. So what we know, if you remember, we have the joint at the top, right? We have the joint of, so this is the joint of E and HI. Okay. And then this can be written up as a product of the marginal times the conditional. And then we divide it by that of the marginal, so we know that this is the conditional of HI given E, which is the posterior, right? Given Bayes' rule. We do that for the denominator as well. And then that will complete, you see, like mathematically, if we use Bayes' rule, we're able to come to this part. So what's interesting, as you can see here, is immediately we can start to cancel out some terms, okay? So in the denominator, both of them is the marginal of E, right? So we're able to cancel it out, okay? And then the next step, once we cancel it out, we're left with, you see, the product of the E given HI times HI over that with HJ. And if I further break this whole product into two products, as you have two terms over here, you see that I can break the first part as the ratio of the what we call Bayes factor. I'm going to define that in a second. And then afterwards, we have the second term, which is the ratio of the prior. So now you can see that if I'm looking at the ratio of the posterior, is what we're doing over here. For doing that on the left-hand side, eventually we're able to express the ratio of the posterior as the product of what we call base factor times the prior, which is the probability of HI over probability of HJ. And this term, as we know, is the probability of, the first one is if HI is true, I'm looking at the probability of my data, right? And the second one is if HJ is true, I'm looking at the probability of my data. So soonish we're going to define those two, called what we call likelihood function, okay, which some of you know, some of you don't, which is fine, but we're going to do a more formal introduction when we get to the Bayesian inference for proportion starting from today. But what I want to show you here is that really, when we're looking at comparing posterior probabilities of two different hypotheses, it boils down to compare the product of the base factor multiplies with the prior belief. So you can have your prior belief, whatever it is, and then the base factor, which is driven by the data as well as the different hypotheses, we will build a model for it so we're able to compute it as well. So eventually, what I want to show you also, the takeaway is that the base rule itself, of course, tells us what the posterior distribution or probability should be, but if you start to compare across different hypotheses, what base rule does tell us is to how we should change about our belief between or comparing two hypotheses after seeing the data. Okay? So it's not helping us exactly like what we should be believing after we see the data, because everything is comparable. When you have HI and HJ, right? And in fact, if you know, here we're just comparing any pair, but we have a whole partition going on up there. Okay, so you can have all kinds of comparison. And what's interesting and overall base rule is helping us is once we start to get data in, which is the E, and because of base rule, we're able to express the ratio of the posterior as the product of the base factor and the prior belief. The prior belief is whatever you have before, and that's before you see the data, so that is prior. And then after you see the data, you start to have this what we call base factor, right? And then that all together can help you change or help you update your belief, and that will be what the change should be. So you have your prior, the change come through because of base factor, and because of that, you update to your posterior probability or posterior ratio. Okay, kind of makes sense, hopefully. Okay, yeah, so base factor and prior beliefs and all that we're gonna see more and more as we come to it. Let me try to put it quick. Does alrighty, okay, it's coming up. Okay, let me finish this part. Okay, and then we can use the big screen. And so again, it tells us how we should change, right? After seeing the data, instead of exactly telling us what the posterior probability of each should be if the goal is to compare across different hypotheses. Okay? So this one really just trying to show you the math as well as you can see a lot of times things get canceled out, and we're gonna see that a lot as well when we learn different type of Bayesian models coming up. So there's certain recurring theme over here that so I want to introduce you here early on as part of the review, but also I guess a preview of what we might see in many other different contexts. Okay. All right, and while it's loading, let me try to go to the next slide because this again a bunch of probability review. Hopefully this looks familiar, and then you're still able to do some of this. This is a table. As you can see, everything starts from the cumulative distribution function CDF. Okay, and we are defining it. So here, the first example or the notation is about the random variable X. The CDF is the probability of the random variable X, capital X, small or equal to some small x value. Okay, so this is defined for no matter whether you're working with discrete random variable or continuous random variable. This one is always true. And then the table below is just different definition and setup when we have discrete on the left and then continuous on the right. So some highlight points, like all of this will be useful, I think, later on when you refer back to this. But I do want to call your attention to, so first of all, for discrete, we call PMF, okay, probability mass function, because we're looking at, as you can see the definition, we're looking at the probability of the random variable taking one of the possible values, okay? And it will be some kind of non-negative probability over here. Whereas for continuous variable, we're talking about PDF, probability density function, okay? And that is actually is defined, it is still this fx, f little x over here, but it's defined through looking at the probability of the random variable x falls into a range or like an interval over here, if it's univariate over here. And we're looking at the probability of this event by integrating over the PDF function within that region. And this is very important to note, just because many of you probably still remember something very interesting about continuous random variable is that the random variable x taking any particular value, the probability of that is 0, okay? Because it's not defined at any particular point, but only if you integrate from little a to little b, for example, with respect to your fx function, you're able to get your PDF. Okay? So keep that in mind. The second rule over here is that for both is well defined, meaning that if you integrate for the continuous case over the entire support, you should integrate to 1 for a PDF, and then for a discrete, you are summing over all of the possible values, which should sum up to 1. Okay? CDF, again, going back to before, but we are able to also talk about them in terms of the discrete and continuous. One thing interesting, I guess, the important relationship over here is that to get CDF, or I should say to get PDF from CDF, you do differentiation, okay? And from PDF to CDF, you're doing integration. So these are also important reviews over here. And lastly, for expectation, and this is useful later as well, especially as you know, when we did that toy example, I should say like the all-nighter example in class, right? We're looking at those cases where we're working with discrete random variables because we have discrete number of cases of those guesses and all that. So we're doing summation, whereas if you're working with continuous random variable, you're doing integration. So similarly for expectation over here, we are looking at the summation of all possible x of x times fx, whereas for continuous, it's still x times fx, but you're doing integration to get the expectation. Okay. Lastly, if you're working with a function of x instead of random variable x itself, you're able to use this handy expression. If my function is called gx, then in order to get the expectation of gx itself, I'm still doing a summation for the discrete random variable case, and I'm just doing gx times fx. Okay. Whereas if I'm doing it for the continuous case, I'm doing integration of gx fx. Okay, hopefully this still sounds familiar and feel comfortable about all of this. Okay, so this could be handy when you come back to this. So that's why I tried to make a table, hopefully as clear as it could be. And then lastly, I also want to mention, and this will be very relevant as we go on as well, is that we're not only care about the marginal, but also the joint and the conditional when we're working with probability in terms of, and distribution in terms of Bayesian inference. And we have seen some example already, right? The Bayes rule itself comes from the joint divided by the marginal, so you can get a conditional, right? And then there are a lot of back and forth, A given B, B and B given A, in that kind of context. So I want to review this as well. So for the joint, we have the joint PMF for the discrete and joint PDF for the continuous. Marginal, just like what we did, and this is relevant to one of the weekly checking questions as well. When we were doing Bayes rule earlier, we're summing over one of the variable of the joint to get the marginal of the one of the other variable, right? So remember, we did the Bayes rule, what, like the probability of, I'm just gonna say this very generically, of A and B over PB, right? So what this relevant is how to get that margin of PB. For the toy example, we split up, right, into the cancer and no cancer case, right? And then we get the joint and then sum them up in order to get the marginal. And that's exactly what this review is about. When I'm trying to get the marginal of one of the two variables, it is equivalent if I'm doing the discrete case, if both of them are discrete, it's essentially I'm summing over the joint distribution of the two over with respect to the other variable in order to get the marginal of x. Similarly, you can do that for y. And you will see also when we get to continuous prior distributions and all that, we will start to, instead of doing summation, we're going to start to do integration. Okay, so the review part of this is if I want to know the marginal distribution of x, and I happen to have the joint of x and y, what I need to do is I need to integrate the joint with respect to y to get x. Similarly, you do that with respect to x to get y. All of them, you can see the analogy going on. But then for discrete, you always do summation. For continuous, you always do integration. And that's why the Bayes rule, we have two versions. Okay, we'll have the discrete version, which is what we saw before. And we're also going to introduce the continuous version as we move on. Okay, so all of this actually has this, I just want to say it has this background from probability review. And then lastly, if you're looking at the joint CDF, then usually I think in probability course at Vassar, we usually try to work with the continuous case. So you can define it from the joint. So from the joint PDF, you go to the joint CDF by integration, double integration in this case. Okay. And then if you want to get to your joint PDF, you go from double differentiation in this partial differentiation twice from its CDF. It's from its joint CDF. Okay. All right. Good. I know this might be a little bit dry, but we need to go through this because later on things will get a little bit easier because we can refer back to this. With marginal and joint, now we can define conditional distribution, which is also part of the review. The general form is at the top. If you have x given y, the conditional distribution that you want to get is going to be the ratio of the joint of xy over the margin of y. The joint density, as we know, can be written as the product of the marginal and the conditional. So there are two ways you can do it, right? You can either get the margin of y and multiplies with x given y, or you can get the margin of x and get the and then multiply with the y given x. Both of them gives you the joint, and then you can see that Bayes rule is really playing with different conditional distributions. Okay, sometimes you put x in front, sometimes you put y in front, and of course, when we get to parameters and all that, it becomes the theta and then becomes of y, which is the data. All right, with that, I just want to also show conditional expectation. We won't talk about like the detail one more time, but you know, for summation, you do that for discrete, and for integration, you do that for continuous. The same for the variance as well. And we do have this handy two of the handy expressions, the law of total expectation, as well as the variance, conditional variance formula. Okay, so I won't spend too much time on this, but I think just to show you that this should have been covered in the probability course, and this could be handy as well when we deal with certain context coming out. All right, now it's the transformation. So I think the computer is coming back. So I will talk about the general method and then give you the time to work on the exercise, and then I will switch back to the computer so everybody can see the screen in person at Vassar. So transformation variables, this is the case that let's suppose I have a random variable that I know is PDF. Okay, and all of a sudden I have a function of this variable. I want to know how to derive the PDF of this function of the variable. Okay, so this is which if you started doing the homework, like I said, it's relevant, and then it could be relevant in other contexts coming up as well. So we're going to do a little exercise with the review of the derivation method itself. So suppose x is a continuous random variable, the PDF is fx, and then we come along having a gx function. So this is a function of x, and let's suppose this function is monotonic and differentiable. Then we are able to have a handy expression of trying to come up with the PDF of y. So here what we say is the PDF of y equals to the PDF of x times you can think about it as the absolute value of dx over dy. Okay, so this requires you to compute the dx over dy and then take the actual value of it and then also multiply that with the marginal PDF of x in order to get the marginal PDF of y. The reason, or I should say more rigorously, is we can have, so whenever we try to get dx over dy, it requires you express x in terms of y. Right? So that will be the inverse function of g. Okay, so g, if you remember g, so y equals to gx. Okay, but the x will equals to negative or inverse of, inverse of y. Here, yeah. Okay. So if y equals to gx, then x is g inverse y. And once you get the inverse function, you're able to take dx over dy. Okay, take the first order derivative. And then that will give you your absolute value of that expression. And then you're able to multiply that with the margin of x. And notice here, the margin of x will be expressed in terms of y. Okay. So maybe to recap a little bit, the left-hand side we're trying to get the PDF of y. So of course, in the end, everything is about y. Okay, whatever the answer you get should not have any x in it. Okay, we need to think about it as a change of variable and try to figure out what it look like. So the formula that this review is about is that you need to get the dx over dy, meaning that you need to express x in terms of y and then take the first order derivative. But also whatever is given to you about the PDF of x, you need to express it in terms of y. And then you take the product, and then you should be able to get your answer. Okay. So let me get to the exercise and give you the time, and then I can spend the time to set up my computer finally, okay? So the example is, let's just say x is a uniform, continuous uniform, okay? So fx equals to 1 when x is between 0 and 1. That's what this sentence is about. The question is, what distribution does y equals negative ln x have? You can use, so by the way, this is the gx function, okay, just to help you set up. And then what we reviewed just now is that if this gx function is monotonic and differentiable, then you're able to use this formula. So take your time, and I would just say, like I said, this is saying fx equals to 1 if x is between 0 and 1, and 0 otherwise. I'll give you the time to work on that, and I can then get my computer hopefully working, and then we'll continue from there. So take your time, and then you can work with your neighbors. And for remote students, once I be able to see you, I can get you breakout rooms and all that as well. So just give me 1 second. All right, hopefully some of you made some progress and then get the chance to talk to your neighbors to see maybe where you are stuck at. If not, maybe you already got the final answer. And like I said, I post the slides and the solution just in next couple of slides, but always try to, I guess, not to look at them while in class and then use it to review. I think that would be best. Nevertheless, for us, we have this gx function to be negative ln x, okay? And then we need to, so that's the gx function. As we know, in order to use this formula, we need to have dx over dy, meaning that we need to find the g inverse function, which is y, which is x in terms of y. And then you're able to take the dx over dy, and then you can also then later on plug in into making your expression working. So with that in mind, let me show you. First of all, we check this gx function, which is negative ln x, and it is monotonic and differentiable, and that's what this figure is here for you to just to get a sense, okay? So because of that, we are able to get the inverse function, g inverse y. So that is, we know that y is negative ln x. So if I take, in this case, I guess, exponent both sides and rearrange the terms a little bit, I will get my x equals to e to the negative y. So this should be straightforward, a algebra problem. And then, because now we express our x in terms of y, we can take our dx over dy, okay? And that's just differentiation rule. So we know that dx over dx is ex itself, okay? Right? With the knowledge that we know before, right? And then also we have a negative y over there. So it's a chain rule, okay? Don't forget that you have that negative y. So eventually you're gonna get dx over dy to be negative e to the negative y. Make sense? We all get to this point? Okay, all right, that's good. So
recording in progress.
That's a disaster, sorry. All right, give me. I don't think. All right, I cannot make it work, so let's just use this one. Sorry about that. I will fix it next time. All right, so we get the dx over dy, and then the absolute value of that is e to the negative y, right? So we get that part of the formula working. So the next question is, as we know, if we come back to the method, as we know, we have this fx that we need to figure out what it is. Okay, so this fx, we know the PDF of x that I wrote earlier already, but it's in terms of x, so we need to make sure that it's in terms of y. Okay, What's special in this case is that even if it's in terms of x, it's already a constant. Okay, it's a constant between 0 and 1. Fx equals to 1 because that's the uniform 0, 1 case. So this is actually maybe a simpler example than what you might be working on for the homework, but the general idea is the same. So the range of x, the range of y, as we know, which is what Noah's question earlier. So x is between 0 and 1. Okay, and then y is negative ln x. Okay, and just like the figure that we did earlier, you can see that the range of y is everything positive. Okay, so when you're working with this new random variable, the PDF of it, you need to make sure that you know the range of y itself, which is everything non-negative over here. And then the fx, like I said, is the simpler case because it's always just going to be 1 in that range. Okay, so this whole thing becomes 1, and you take the absolute value of negative e to the negative y. So eventually, your fy just become e to the negative y. Make sense? Make sense? Yeah. So like I said, it's easy in this case because fx itself is a constant. So it's not about x itself. It has no x in it. It could be, we won't do the exercise in class, but I just want to show you that it could be your fx. I don't know what it is, but it could be some kind of x squared, let's just say. Okay. If the PDF of x is something like this, then you need to figure out how to express the fx x squared in terms of y. But overall, it should be straightforward because we know that y is negative ln x, right? So you simply just replace your x in terms of y, and then plug that in, you get your whatever formula in the end that you're gonna have. So the homework question, I think, is something a little bit more complicated. This, we don't have a constant going on over here. But otherwise, the general method is the same. So we got a question. The good thing using iPad is that I can see the question up here. So Koji's question is why we have fx equals to 1. Okay, so this is because if I go back to the question itself, because x is a uniform between 0 and 1. So what that means is that fx equals to 1 when x is between 0 and 1, and it's going to be 0 otherwise. And if we want to do a quick review of uniform distribution, if x follows uniform a to b, okay, what that means is fx is 1 over b minus a if x is between a and b, and it's going to be 0 otherwise. Okay. So because x is uniform from 0 to 1, so we simplify that into this directly. Okay, Carl, did you have a question too? Yeah.
Yeah, when we define a uniform distribution, is the range x inclusive of 0 and 1?
Oh yeah, good question. So what do y'all think? The question here is that, okay, I wrote between 0 and 1, and Carl's question is, can we also do, let me use a different color. Can we include 0 and 1 as well? Okay. Any thoughts? Anyone thinks we should include it? Not included? No idea? Okay, not include, okay. Yeah, so a quick answer to that, which will be also be a good quick review over here, is that as we know, when we're working with continuous random variables, at any particular point, it doesn't really matter if you include it or not, because at that point, the probability is always 0. Okay, so in fact, for this uniform 0, 1 case, you can have x greater or equal to 0, smaller or equal to 1, or maybe one of them is open, the other one is closed, or both of them open. That's all fine. But it doesn't affect, I think, the final results. Yes?
But in this question, the range of y is dependent on the range of x.
Good point.
Solution, you wrote that.
Yeah.
The range of y is inclusive 0.
Mm.
The uniform distribution is not 1.
I see. So you're saying, okay, so the question here is our x is, okay. If this is the case, then what do we have? Because ln x gonna be between greater than negative infinity and up to 0, right? Right? If x is between 0 and 1, then ln x is greater than negative infinity and smaller than 0. So if I define it in this way, so good call, Carol. Because if I strictly say x is between 0 and 1, then my range of y should not include 0. Make sense? Yeah. And right, so that's a good comment. I think I need to fix it. And but we all, I think, understand the concept overall. And then, of course, add the endpoints. It's a little bit tricky. For us, I think we can go either way. But the main point over here is how to do the transformation, how to use that formula, how to check the condition, monotonic and differentiable. And lastly, how to apply the formula so we're able to get the PDF of y given the PDF of x. Okay, okay. All right, that's good. So a couple of other things. Yeah, later you probably would learn also that when you have y to be the PDF of y to be e to the negative y, it's actually exponential random variable with lambda, the parameter equals to 1. Okay, but for us, as long as you know it's e to the negative y, I think, and now also the range of y correct, then we're all good to go. All right, a couple of other things, then we can start the new chapter. Okay, so independent random variables, which will be very useful later on, because so far we're just saying that, especially with the binomial, like the success and failure, the examples that we did the other day, it doesn't say as much. But as we know, a lot of times in practice, what we get is a sequence of observations. Okay, and then a lot of times the data model that we're gonna describe or construct with gonna have what we call independent random variables. So I want to do a review over there and then just show you overall how we understand it. So suppose y1 through yn, they are random variables and they share the same random distribution over here. And theta is the parameter describing how they're generated. So in that case, we're gonna say y1 through yn to be conditionally independent because it's conditional on theta itself. And then we're able to write the joint CDF in this case, in this form. So on the left-hand side, we have the joint distribution of y1 falls into the range or region of a1 up to yn to the range of an, because they are independent from each other. So we're able to write the joint in the terms of the product. Okay, and each of the product, as you can see, is about a particular yi. And we call this conditionally independent. The conditionally part is only because they're all conditioning on this theta. Okay, so that's one thing. And more commonly, you're going to see something like this. If I want to write out the joint distribution of y1 through yn, and I know they are independent from each other or conditionally independent from each other given the parameter theta, then it's equivalent of writing. So this, again, this is the joint PDF. Okay. By the way, up here, this is the joint CDF. So with that in mind, the joint PDF, as we reviewed earlier as well, if they're conditionally dependent from each other, it's going to be the joint, or the product, I should say, of all of the marginal together. And that's why eventually a lot of times we use this big pi, which is the product notation. So we're able to get the joint CDF as the product of all of the marginal CDF. Make sense? Make sense? Yeah, so whenever you have conditional, in this case, conditional independent, whenever the variables are independent from each other, you can get the joint through the product of the marginal. And in this case, everything is conditional on that theta. So with that in mind, I have another little exercise for you. Oh, sorry, another little exercise just coming up. So lastly, you probably know this IID, right? Independent and identically distributed, this concept. So they all follow the same distribution and they're independent from each other. So we can call them conditionally IID, just as a one step further from the general IID key. All right, so the exercise here is, let's suppose I have a sequence of y's. Okay, they all follow a normal distribution, the same IID. They share the same mu, they share the same the sigma. Please write out the joint density of y1 through yn. And I give you the normal PDF over here. So this is going to be a little bit more like an algebra exercise to make sure that you know what terms go into the different parts of the final equation. So give it a try. The previous slide talks about the joint PDF, how to get the joint from the product of the marginal. But this is a specific example of all of the marginal here. All of them are the same normal. So I want you to give it a try to write out the joint of all of them given mu and sigma, those are the normal parameters. So give it a try, and I will call, yeah, we'll talk about it, look at the solution together in about a few minutes, and feel free to check in with your neighbors as well. I highly recommend you to write it out one by one and then do the little exercise, because you're gonna see that we do a lot later on in this course whenever we have, you know, complicated or maybe not so much complicated data model. And then we need to do some kind of algebra over here to make sure that we can work through the posterior distribution. So take a moment, and we have the answer coming up in about a few minutes. Okay, let me talk about maybe the first couple of steps and then give you the time to finish the rest. So we can be on the same page. So here, if we come from the previous result, we know that the joint is the product of the marginal, okay? And each of the marginal right now is a normal density, and we know the PDF of it, given it. So essentially, we're applying this result and trying to get the joint of y1 through yn by the product of all of the marginal. Each marginal is the same, actually, in this case, of a normal. Okay, so well, I guess my solution comes out all together, but that's fine. So the joint, okay, as we know, is the product of the marginal. Each marginal, as we know, so each yi is a normal mu sigma. Okay, so what that means is that in order to get the overall joint coming out, we have the product, so you keep the product in the second step, okay? But in the product itself, you're getting each of the normal density. And we know that the PDF of a normal is this complicated form, okay? They share the same 1 over square root of 2 pi sigma squared. And then in the exponent, the yi is different. Okay, so we need to factor that into it. So you see that generically, we have this 1 over square root of 2 pi sigma squared. And then in the exponent, we have negative yi minus mu squared divided by 2 sigma squared. And then all of this, nothing is about y, or yeah, nothing is about the product itself. So you can raise the whole thing to the power of n, because you have n copies of it. Okay, so that's what the first term is about. And the second term is essentially summing up all of the terms in the exponent. Okay? So later on, when we get to the second topic of Bayesian inference for a mean, we're going to see how to further decompose this whole complicated thing over here, because there are certain terms that we can express furthermore. But right now, as long as you know how to get the product of the marginal to the joint for a normal example like this, I think we have enough to review to move forward. Okay. So the key here is that we have one part of the normal density is independent of the yi. So you are just multiplying the whole thing n times. So you have this 1 over the whole big thing to the power of n. But then in the exponent, you're producting all of the exponent, but that is equivalent of summing up all of the terms in the exponent itself. Okay. So like I said, this is mostly like an algebra exercise, but it's useful. And then you might come up, like I said, will come up later as we do a little bit more of the Bayesian inference exercises. Another concept I want to mention, we don't encounter it as much, but a lot of times we might not care as much as the index of the yi when we have a sequence of y1 through yn. We call them interchangeable or exchangeable from each other. So as long as you have y1 through yn, the index of the 1 through n a lot of times doesn't matter as much. And when that happens, we call that y1 through yn, they're exchangeable from each other. Okay, because at the end of the day, we just care about the joint. Okay, no matter what the order is, we are getting the joint itself. So with that in mind, I want to wrap up this part, because a lot of times you're going to see something very similar like this. Okay, we have a sequence of observations. Okay, the data model going to say that it follows a p distribution, whatever that is. It was a normal when we looked at the example. Okay, and then of course for us, we're going to have our prior distribution for the parameter, which is right now we use p theta over here. And then with that, we will be able to do a lot more of the different modeling techniques that we are able to talk about. Okay. Okay. All right. So sorry about the delay and everything. I think we have 15 minutes, so I can start the next lecture. And the slides is on Moodle, so you should be able to put it up. And let me